started, we're going to start with a short video that I think will give us some backdrop for my talk.
December 10th, 2019 will be a date that goes down in history for MagniX, for the aviation industry, and I think for the world. It's the day that the first commercial aircraft flew all electric. Take one.
I think, you take a step back and you look at what had to be done. We had to create a high-torque motor, merging the best of high-performance technology with the requirements and challenges of an aerospace environment in a time frame that people keep consistently saying couldn't be done. And how we overcame that was by not running an individual race, but by building a culture that says, all right, people say things can't be done. We're going to challenge that in order to produce something remarkable.
All the team here, it's midnight.
Guys, first electric flight is the next step in allowing aviation to go all carbon neutral.
Oh, it's amazing.
It's always ready, especially with this aircraft.
If something is worth having or seeing happen, then it's worth working for. I'm at the Harbour Air Facility in Vancouver, Canada, looking at our aircraft. This is the Electric Beaver, and we're going to be doing a few tests today as we get ready for our first flight next week.
Every day we seem to just have these big problems that we had to overcome, and there were some hard days. Oh, it's failed this test, and you just think like, how is this going to come together? But that's when you sort of fall back on the team that you have with you. It's one thing to be able to solve technical solutions, and you've got a lot of smart people in the same room, but it's another thing to get through it as such a bonded team, to still have that by the end of what we've been through.
We're on the dock, and the plane's about to be pushed into the water. I don't know if you noticed, when that plane taxied out and took off, there were no fumes, no exhaust, no smell, zero emissions. December 10th, 2019 will be remembered as the day the electric aviation age started. That team made history. This doesn't happen much in a lifetime, where you can actually look back and say, we were part of something that truly changed the world. And it did, and it will.
Okay, so I see that. I'll tell you, it's probably the 150th time I see that video, and it brings tears to my eyes every time I see it. It was an amazing, amazing year to pull that off, and to see the actual aircraft fly was unbelievable. So let's talk a little bit about what's going on. Just want to make sure everyone can still hear me okay?
Yep.
Okay.
Yep.
Sometimes hard to figure that out. Okay, so the first thing is to address the elephant in the room, and that is to make clear batteries are not the same as fuel. Fuel is 40 to 50 times more power dense, more potent than batteries are. There's a reason you can't light a match next to a gallon of fuel. It's not a joke in that when people say batteries will never take you as far as fuel, they're absolutely right. And anyone who tells you different either doesn't know what they're talking about or is lying to you. Batteries are not as good as fuel. But that really isn't the question that's in front of us. because if you think about the car industry that actually started the move to electric transportation, if you take away kind of rail that slightly started before with connected electricity, if you look at the car industry, Tesla was told the same thing 9 years ago. Batteries are not as good as fuel. You'll never have a family car that goes as far as a fuel car does, et cetera, et cetera. And they said, that's true, exactly the same thing. And they started with a 2-passenger car that could go probably, around 80 miles. And then from there, things started to progress. Today, I have a Kia Niro electric that can take my family of 5, 280 miles. That's the same as any internal combustion engine car, except I don't have to pay a dime in fuel, nor do I have to do any service. And so in a span of 9 years, we went from it's impossible to now it's normal. At least here in the Seattle area, in a lot of the United States and a lot of the world today, no one turns their head anymore when they see a Tesla or a Kia Niro electric, et cetera, drive by, and no one turns their head to see a charger in front of a store or a mall. It's now commonplace. We believe, from what we're seeing, the same thing will happen with electric aircraft. So let's talk about why we're actually here. And that is that middle mile aviation is not working. And we define middle mile aviation as flights or transportation between 50 miles to about 1,000 miles. If you look at the transportation in general, you could probably split it up into about 3 sectors. One is what we could call in logistics first or last mile, right? It's that 50 miles that are within an urban area, within the city, within the neighborhoods, where you'll do your commute to work for the most part, where you'll do that last delivery from Amazon Prime, et cetera, et cetera. And while we may not like all the alternative transportation modes there are plenty, from walking to the electric scooters and bicycles that you find in a lot of the cities, to cars, Ubers, Lyfts, taxis, subways, light rail, et cetera. Again, we may not like them. We may not like the traffic, the congestion, the pollution, but there are plenty of alternatives. And for the most part, they're pretty efficient. The other side of the spectrum is transportation or travel above 1,000 miles. Seattle to New York, Seattle or New York to London, where your really only alternative is either rail, that for the most part doesn't exist, definitely not in North America. Maybe if you're lucky enough to live on some of the routes in Japan or China or Europe, if you are lucky enough to live on one of those routes of fast rail, you have an alternative. But for the most part, it's either fly or, for example, US to Europe, take a ship that might take you 2 weeks or 3 weeks to get to. So that's interesting. Some people might be able to do it. Most of us don't have the time or the luxury to do that. And for the most part, flights above 1,000 miles are fairly efficient. If you think about having to travel from Seattle to London, I would have to drive 45 minutes to SeaTac Airport, the only airport that has international flights or long-haul flights. So drive 45 minutes there, get there about an hour ahead of time, get on a 9-hour flight, arrive at London Heathrow, and drive another 45 minutes to an hour into the city. And I would pay in coach probably $600, $700, maybe $800. That's not bad from a time and cost perspective. That's pretty good. The problem is, or the challenge comes in the distances of between 50 miles to 1,000 miles. Seattle to Pullman to go visit my daughter at Washington State, for example, University. Seattle to Spokane, Idaho, cities within Idaho, Portland to San Francisco. Those short haul distances where it's really long to drive. We're talking 2, 3, 5-hour drives. For example, Seattle, Spokane, Seattle, Pullman is a 5-hour drive. Or you're looking at flying for 45 minutes, but really expensive. I like to give the example again of my eldest daughter who's studying mechanical engineering at Washington State University. Pullman is 230 miles away from Seattle. And there are flights there. It's a few flights a day. One airline flies there. It's a 45-minute flight. And to do that 230-mile flight return is $484. $484 for 45 minutes and a 230-mile trip. Most people, me included, when I want to go visit her with my other 2 kids and my wife, there's no way I'm paying $2,000 to fly. So we drive 5 hours there and 5 hours back. Clearly not efficient, clearly not convenient, clearly not good for the environment, but it beats $2,000 and polluting in a much higher fashion with an aircraft that's way overly built to fly 230 miles. And so the alternatives for middle mile are not very good. Most of North America doesn't have rail. And so the average American will actually drive 4 to 8 hours instead of flying commercial, because the average American also lives about 45 minutes from a major airport. There are over 10,000 airports in the United States, but the airlines only use about 600 of them. Why? Because when the airport system was built in the 30s, 40s of this country's existence in aviation, the idea was that airplanes would be that next connection to the frontier. Rail connected Eastern U.S. to the New West, right? When the movement west happened, and anywhere rail went, there was a boom in that area because it allowed people and cargo to move much more efficiently than either car or carriage at that time. And when aviation came to its own to become an industry, the belief was that would be that next boom in the United States, in North America, and in fact worldwide, where planes would arrive to a town and allow, again, the movement of cargo and people in a much faster and more economical and efficient manner, thus creating additional boom. But the industry learned, and airlines learned, that the bigger the airplane, the more money they make. Now, I'm not saying that there's something wrong with that or that airlines are greedy and that's not okay. Airlines work in a profit margin of anywhere between 0 to 5% in a good year. It's really expensive to be an airline and to operate aircraft. And so when they can take bigger aircraft in order to ensure better profitability, they do that. The challenge with that is that the bigger the airplane, the more you have to fill. For example, to break even on a 737 or A320 or 767, to break even, you need about 70% of your plane to be full on its flight. 70%. On a 100 passenger plane, that's 70 people. On a 150 passenger plane, that's about 100 plus. That's a lot of people. And so in order to make money, you have to delegate yourselves or limit yourselves to flying from large metropolitan airports. That's why in all of Washington State, you can really fly from a handful of airports if you want to fly anywhere outside of Washington. SeaTac to go anywhere serious, and then a few others. They're Painfield a little bit, Spokane a little bit, but that's about it. And the reason is, if you want to fly anywhere far, it's a big airplane, and a big airplane has to come to SeaTac because that's how they make money, one. Two, the logistics needed for that big airplane are significant. The baggage handling, the catering, the gates, et cetera, et cetera. And so the transportation and specifically aviation model of middle mile is broken. It's not working. Now the question becomes, well, does anyone want to go shorter than these long distances? And the answer is the data speaks for itself. This is 2018, what's called OAG data. It's the main source of airline data worldwide. And for 2018, which is the last full year of data that we have, you can see the numbers here. Worldwide, there were almost 39 million flights around the world done by traditional, what I'll call scheduled airlines. So I'm not talking about the little Kenmore Airs or Harbor Airs or Cape Airs. I'm not talking about those guys. I'm talking about the Alaska Airlines, the Horizon Airs, the Uniteds, the Qantases, the British Airways, the large scheduled airlines. They flew almost 39 million flights in 2018. 75% of those were less than 1,000 miles in range. 75%. That's less than the distance to cross half of the United States. 45% of those, almost half of worldwide flights, were less than 500 miles in range. 5%, almost 2 million flights, were less than 100 miles in range. Now, if you think about that, that's an unbelievable number. The 737s, 757s, A320s, these aircraft are optimal at 1,500 miles, 2,500 miles. They get optimal, these large jets, in cruise at high altitude. So they take off, climb to altitude, burning literally tons of fuel, creating an absorbent amount of emissions to get to cruise. At cruise, they're pretty efficient. They're very fuel efficient. They don't create that much emissions. They create a lot, but not that much relative to what they're doing. And they fly fairly efficiently. But the problem is when they're not flying 1,500 miles, rather they're flying 200 miles, guess what? You get all that burn and emission from the climb, but by the time you get to that efficient altitude and cruising, You suddenly hear that bing, we're about to start descent, please fold your table and close your laptop. So you get no efficiency. And so the majority of flights worldwide are inefficient in the use of their resources. The airlines may be making money, but very little of it, and it's very harmful for the environment. The same thing goes with cargo. If you look at cargo just here in North America, where a bulk of the cargo is flown, between 0 and 1,000 miles, there are almost 700,000 flights a year. And these are all done by propeller planes that burn either leaded or unleaded fuel. And yes, there are a ton of airplanes that still burn leaded fuel into our environment. And they're done at flight hour costs of $1,000, $1,200, $1,500 an hour to fly. That makes your package delivery expensive. If you read reports, for example, on how much Amazon spends on deliveries, it's billions. It's crazy. And so the market for short hop flights is tremendous. That's why we exist, to connect communities by enabling every person in the world to fly. Now, the only way you can connect communities in short distances and really allow people in cargo to connect in a very efficient manner is to lower the cost of flying. The flying today is expensive. So if I want to be able to go visit my daughter in Pullman and fly there for 45 minutes, which if you think about it, what does that mean? If I could fly in 45 minutes there and back, I could go visit her for a day and it wouldn't be hard. But I'm not going to pay $484 for that. What if I could do that for $50? I would go visit her without hesitation. My whole family would go. She would come visit us on the weekend without hesitation. Flights would be full, but they would have to be at a cost point that makes sense. Suddenly going from here to Walla Walla for a wine weekend is not a big hassle. Flying from here to Portland is not a big hassle. Imagine if you could live 150 miles away in a small town like Ellensburg with a phenomenally great quality of life, low cost of living, no congestion, but you could still work at Amazon or work at Microsoft or work at Real Networks or at PACCAR or at Boeing, but instead of driving 2 hours from Ellensburg over the pass, if it's open, to get to Seattle, or instead of traveling, for that matter, an hour from Bothell to Seattle through traffic, what if you could fly for 15 minutes and pay $25, $30? That might change the way we think about a suburb. So costs have to be reduced. And in today's world, the only way to reduce operating costs of an airline is to go electric, because fuel and the maintenance of the internal combustion engines on the aircraft today are anywhere between 30 to 50% of an airline's operating cost per flight hour. So you have to eliminate that, or all but eliminate it, in order to make flying reasonable. So who are we? Team of phenomenal people. We're today about 60 plus minus people, split between two main locations, one on the Gold Coast of Australia, which is a lovely, lovely place, and the other here in Redmond, Washington. And we've been able to pull in phenomenal people from the giants of aerospace and technology to come in and basically focus on changing the world. So what is it that we've done? We've developed basically an electric propulsion system for airplanes. We did not invent the electric motor. The electric motor has been around for a very long time. What we were able to do is design the motor and the inverter, the power electronics that go with it. We've been able to design them in a way that allows for a few things to happen. One is a very powerful or very high power to weight ratio. We're able, for example, to develop 375 horsepower in a motor that weighs about 120 pounds. That's pretty significant. That's one aspect of it. The second is that motor only turns at 1900 RPM. A traditional engine to reach those types of power at weight will be turning at 10,000 RPM, 15,000 RPM, even 20,000. Ours turns at 1900. Why? Because 1900 is the speed at which a propeller on an airplane turns, plus minus. It turns at those low speeds because you can't turn it faster, because if the tips of that propeller turn any faster, they'll pass the speed of sound which will basically destroy them. And so you have to maintain that lower speed of the propeller. So what do traditional propeller planes do that you'll fly on today if you go to Pullman, for example, or to Vancouver or to Portland? What happens is those engines turn fairly fast, and then they have this giant, maintenance-prone, expensive, heavy gearbox that takes the shaft from 10,000, 15,000 RPM down to that 1900. By being able to design the electric motor like we did that creates full power at 1900, you've eliminated that gearbox, direct to propeller connection. So that eliminates weight, it eliminates maintenance, etc. And then the third thing we're able to do is have it all done in a liquid-cooled system, because if you think of how airlines operate, high altitude, longer flights, lots of power, that will create heat in these motors, and you have to be able to cool it. But if you were to use a traditional cooling system, the weight penalty would be so significant that it wouldn't be worth it anymore. And so we've been able to do it with a lower weight integrated liquid cooling system. So that's kind of the key of what we've been able to do. And I don't know if surprisingly enough or not, but basically we're only one of 2 companies in the world that have been able to do that. The other is a small company out of the UK you may have heard of called Rolls-Royce. They're only one of the 3 largest and most significant aviation propulsion companies in the world. They and MagniX, a small company here in Redmond, are the only 2 in the world that have been able to crack the code, if you will, of building an electric motor powerful enough to produce that 300 plus horsepower. Within that, we're the only ones who've been able to actually do a 560 kilowatt or 750 horsepower motor, and in fact fly it on a commercial aircraft, which is what was mentioned earlier. We flew for the first time back in December 2019, so 5 months ago. We flew it up with our partner Harbour Air, which is a regional airline out of Vancouver. They're the world's 2nd largest seaplane airline, and they flew that Beaver for the first time. It's a 5-passenger aircraft, flew it in December. And I mentioned a little before this meeting, we've been flying it ever since, continuing test flights. In fact, this week it's still flying up in Vancouver. So these are just some interesting specs. I won't go through them. You can see them later on, but basically really high power, really high torque, low weight, low speed. And the nice thing about electric motors is that, one, you can get that full torque at really low RPMs. If you've ever ridden or driven in an electric car and you put your foot down on that power pedal, on that gas pedal, to use the old school term, you feel that torque sticking you to that back of the seat going forward. The torque is instantaneous. Well, the same thing happens on a plane. Instead of that rev up that usually goes on when you take off from a traditional aircraft, they can get on an electric plane immediate torque. And so that means that, just like we saw in these test flights that have been going on, you can take off in a much shorter runway or a much shorter river. You can climb to altitude much faster, so you can get away from any noise environment or building environment or any type of restriction. You can get away much faster, and you can fly into and land and take off from much smaller airports. So imagine now a 5, 9, 12 passenger aircraft that can fly in and out of these small airports that are in our towns as opposed to the main hub airport. And we can do it, instead of at a $200, $400, $800 ticket, for $30, for $50, for $70. Imagine not having to stand in line with hundreds of other people in the TSA line at an airport, instead with 5 other people, and there is no TSA line. Because an aircraft under 19 seats, you don't have to have a dedicated TSA checking capability. The pilot is responsible for that. So being able to provide these amounts of power at these amounts of capability at low operating costs really changes the way we think of aviation. Now, why are the operating costs so much lower? Well, the reason is that there's no fuel, there's electricity. To give you an anecdotal piece of information, take a 9-passenger aircraft. If I fly that traditionally today in an internal combustion engine aircraft, that will cost me anywhere between $1,200 to $1,300, all the way up to $1,500 an hour to fly that aircraft, really depending on the price of fuel at any given day. If I fly an electric airplane, that same 9-passenger aircraft electric, we're talking about $200 to fly that per hour, $300 maybe. And so from that perspective, we're looking at phenomenal and really powerful changes in costs, right? We're not talking about 5 or 10%. We're talking 40 to 80% lower operating costs per hour. So that really drives two things that can happen. That can drive operators to say, I can now, with that added profitability, take on more aircraft and fly from and to more airports, commoditizing flying. I can also reduce my ticket prices significantly and still be making more money. Again, commoditizing flying. So suddenly we can change short haul flying, again, 50 to 1,000 miles, no more than that, but commoditize it to a point where that type of flying becomes the same as taking the bus. Suddenly, instead of paying $70 for a bus ride from Pullman to Seattle, which is what my daughter pays, because we're not, again, $484 for a flight is a little much. But instead of paying $70 for a bus ride, what if you could pay $70 and fly? Maybe $90 and fly. Would that change the way people transport? So again, opening up the ability to move people and goods in a complete different way. And that's why we're going to market in 3 different ways. One is that middle box there, retrofitting, or what we call magnifying existing aircraft. Taking aircraft like the Beaver with Harbor Air, like a 9-passenger Cessna Caravan, tried, proven, loved aircraft today, that the challenge with them is they burn a lot of fuel and create a lot of emissions. Gut that system out, put in a clean, lightweight, low-cost electric propulsion system, and now you have an electric aircraft. It's cheaper to do, it's faster to do, but there's a downside. The downside is these aircraft were built around internal combustion engines. That's why the propeller is a big propeller up on front. And they were built to carry liquid fuel that can go in small tubes around the airplanes or in the wings. They weren't built to carry batteries. And so you're restricted by how many batteries you can take. And since what I started with is batteries are 40 times today, 40 times to 50 times less energy dense than fuel is, you're restricted by range. So for example, this Beaver, instead of being able to fly 600 miles on a full tank of gas, can fly 100 miles with batteries. And so that's the downside of retrofitting or magnifying aircraft. But if you're good to fly 100 miles, if you're within that 5% of worldwide flights, 2 million flights a year that are less than 100 miles, you're golden, because you can fly at 40 to 80% less cost per hour. The second path is an inline option, the box on the left, which basically says, let's go to those same traditional aircraft manufacturers and say, hey, why don't you offer your customer an option to get that same aircraft that they love, but in an electric model? Instead of retrofitting themselves, why don't you do it and sell it to them? And then the third option are where the real future is going to lie of aircraft. Aircraft that are designed to be electric. Aircraft throughout history and today have always been designed around propulsion systems. There's a reason the aviation age today is called the jet age. Why? Because of the jet engine. When the jet engine was introduced in 1939, that started to allow aircraft designers to do things that before were unavailable or not practical. Swept wings, which allowed for higher speed, higher altitude. You could put jet engines in the middle of the plane on the wings, or the back of the plane even, where you could get more efficiencies. You don't see jet engines today, or aircraft with jet engines on the nose like you do propeller planes. So the jet engine allowed you to design aircraft differently. The same thing is with electric. The electric propulsion system, for the same amount of power, is about a third of the weight and a third of the size. So you can put it in places that you simply can't imagine putting a traditional internal combustion engine. So that's like the aircraft that you see here in the picture, and we'll see a little bit more of in a second here. The electric aircraft can put pusher motors on the wingtips of wings, in the center of wings, on the tail of the aircraft, and use it in a way that you can make the aircraft itself more aerodynamic. When doing that, you can get, for the same number of passengers and for the same batteries, a lot more range. Let's take the same aircraft that can go 100 miles here. It can take 9 passengers in the Eviation Alice, which is an all-electric aircraft by design. It can take them almost 650 miles. Why? Because that aircraft is aerodynamically designed, and designed with today's technology, to be an electric aircraft. It is built around batteries. It is built aerodynamically for electric aviation. And so you can take, even with today's limited batteries, aircraft to go 650 miles. Now, remember the data we were talking about. 45% of worldwide airline flights were less than 500 miles in range. That means that when this airplane comes to market in around 2022, 2023, so 2 to 3 years from now, you'll be able to fly the same distance that you fly almost half of worldwide airlines with an electric plane, which costs 40 to 80% less. Now let's talk about the added bonus of all this, which I haven't even mentioned up until now, which is the electric aircraft also creates zero emissions. Now, why did I leave that for the end? We are not Greenpeace. We're not an environmental company. We're not doing this to save the planet. We are doing this because this is good business. This means airlines can operate at a lower cost point. They can fly cargo and people at a lower price point, and they can connect communities in a way that have never been connected before. The fact that the only way to really do that is electric, and the fact that now electric is zero emission, is a huge environmental bonus. Places like Europe, they're already dropping ticket sales by up to 10% because of what's called flight chaining. Scandinavia is leading that effort in Europe, and I call it an effort. It's really a movement, which is basically, if you are found touting that you went on vacation or flew somewhere, you are publicly shamed and ridiculed for destroying the planet. Aviation today, airplanes, produce anywhere between 2 to 4% of global CO2, depending on which report you read. 2 to 4%. And according to the number of flying passengers that people expect to happen between now and 2050, that number will grow tremendously, exponentially, which isn't good for our planet. Now, if you're trying to fight that in current technology ways, things like, for example, synthetic fuels, which will reduce 20% of emissions, etc., the challenge with that is that all those technologies are more expensive than what they are today, than operating aircraft today. If I want to buy a gallon of synthetic fuel that will reduce my emissions 20 or 30%, I have to pay more for that gallon than my current traditional oil-based or fossil fuel-based oil or gallon of fuel, which means it's not very attractive for airlines to do. We would love to think about airlines as, thinking about the environment, wanting to do better, but the shareholders don't want that. The flying public doesn't want to pay more. That's why electric is the solution, because electric is about a business case that makes sense, reducing the operating cost because electricity is significantly cheaper than fuel. Maintenance and service on an electric motor is significantly less than maintenance or service on an internal combustion engine. And so operating costs are lower with the added bonus of zero emissions. So just to touch on this last point, because beyond being the CEO of MagniX, I also have the privilege of being the chairman of Eviation, the designer and creator of the Alice aircraft. As I mentioned, a 9-passenger aircraft, 650 miles in range, flying at 240 knots, which is very nice for an aircraft of this size. The equivalent internal combustion engine aircraft flies at about 140, 180 knots. So it'll even fly faster. And the reason I like showing this image is this is a real airplane. This is not a CGI image of what could be in the future. This airplane was debuted at the 2019 June Paris Air Show and is going through and has been going through operational tests. And so from that perspective, this is really happening. The Beaver is actually flying all electric. This Alice is actually a real aircraft and will hopefully fly sometime next year. And we're now working on a 9-passenger magnification of a Grand Caravan, which is a 9-passenger aircraft that's internal combustion. Also, we've gutted it, turned it electric, and that should be flying here next month, assuming no new restrictions come around from this COVID-19 situation we're in. So that's kind of what I wanted to talk about. And now I'm happy to open it up for questions.
Thanks, Roei.
Hi. Hello. This is Vinod. I have a question. So a lot of fuel is wasted currently during taxiing. And is there any approach? I've read about, approaches to put motors into the wheels and then use that for the initial taxiing and the initial takeoff stands to aid in that. Does that help in saving energy?
Yeah, so there are different ideas. One is, like you said, with traditional aircraft, putting motors in the wheels. Guess what? Extra cost, extra weight. Another idea is like these electric, maybe robots or tugs that will actually drag them across the airport. That's an option as well. Extra cost, extra weight for the same aircraft. And even once that plane takes off, that's where the real fuel burn is. That while it is creating emissions and burning fuel on taxi, the revving of that motor or the RPMs are fairly slow. So compared to the climb or takeoff of that aircraft, it's really nothing. So there are alternatives, but they all add extra while not really creating an impact on the big burners.
Thank you.
Hi, my name's Kyle. Oh, sorry.
Oh, go ahead.
My name's Kyle. I was curious, especially when you look at some of the longer end of kind of your mid-range flights, they are mostly serviced by jets that can cruise 2 to 3 times the speed of an electric aircraft. How do you envision that kind of changing?
Yeah, so it's a good point. Again, the speed that they can cruise at, you have to compare that to the distance they're actually going. So if they're going 800 miles, yes, they have clearly an advantage over an electric aircraft, no doubt. And we won't be replacing them for example, routes like Boston, New York, or London, Paris, or Seattle, Portland, right? Routes like that, where you can fill a 737, an A320, a CRJ, and you can fill that aircraft 7, 8, 10 times a day going back and forth. There's really no justification to put a 9-passenger electric aircraft on that route. There's no justification. But what I would say is, and so there's no competition, right? There's not one trying to replace the other. Where the electric aircraft will come in is in routes like, let's say, Seattle, Portland. If you check and see how many people are within 10 to 15 minutes of SeaTac going to somewhere that's 10 to 15 minutes from Portland, versus are they really trying to fly maybe Arlington to Corvallis? Are they trying to get to Eugene, to Bend, Oregon? Where are they really flying to or from? If you're flying JFK to Boston, are you really in the Queens area going to Boston Logan, or are you trying to get from White Plains or somewhere else to northern Boston? And so from that perspective, the data will start to explain and show what are real point-to-point flights looking at. So maybe that same 800 miles, while it could be serviced by a 100-passenger jet much more efficiently, the people on that jet would rather not drive 45 minutes to an airport, get there an hour ahead of time, hundreds of other people with TSA, fly that 20 minutes that's faster, and I'm the first to say that, to Boston only to drive another 45 minutes. Maybe they would rather drive 7 minutes to a small airfield, fly for 40 minutes, double the time, 60 minutes, and arrive 10 minutes away from their destination and pay, instead of $400, $70, right? So the notion of what electric aviation will allow you to do is start to evaluate door-to-door travel, not airport-to-airport travel. And so you're right, if you look at the JFK to Boston, there's no way an electric plane can compete on speed. If you look at your home or office to your destination door, compare that price and time, and you'll start to see a different story.
I have a question about, this is Samir, and I have a question about, you're designing these motors presumably for the airplanes, but what about the market where there's a drones which can carry the passengers? They will have VTOLs, like they can vertically take off, land. They can access not only the airports, but also the heliports. So how do you see that competition, and what's your response there?
Yeah, so if you remember at the beginning of what I was talking about, I described 3 sectors or a breakdown into 3 parts of transportation. The over 1,000 miles, the middle mile, which is where we play in, the 50 to 1,000 miles, and then the last mile, less than 50 miles. The vertical takeoff and landing vehicles you're talking about mostly target that last mile. They're working on, how do I not spend an hour and a half in traffic going to work in a city, in LA, in New York, in Seattle, etc. Right? So they're 2 to 4 passenger VTOLs, they're vertical takeoff and landing, these Jetsons area or era type of air taxi, they're targeting the buildings. They're targeting basically coming to my home, landing in my backyard, pick me up. I go to the vertiport in the office on the top of my building or the parking lot. I land there, and it's all wonderful. And it's clean, and it's in the air. It's fantastic. That's great. And one day, it will happen. I will actually fly them. I have no doubt that I will fly them. But there are a lot of challenges with those aircraft that will delay it way beyond what we and others like us that are doing middle mile. And I'll tell you why, kind of high level. And it's not the technology. The technology is still a challenge. They're using a lot of small motors and small propellers to create lift instead of like a helicopter, one big one, because they want to create less noise, right? These helicopters are pretty noisy, and you won't fly them inside the city. And so they want to create less noise. The only way to do that, smaller motors, smaller propellers. But that creates a lot of challenge. A lot of motors working together, those are hard to fly. There's a reason these small drones have, the good ones, at least the expensive ones, have the ability to gyro themselves and keep themselves stable. Because if you try to fly one of those drones without that stabilizing software, that would be difficult. But guess what? A drone is not a 4-passenger aircraft. The regulatory authority will be very, very tough on software and hardware that has live people in it. I have a small camera drone. I've, let's say, hit a few trees during my flying. Nobody cares but me and maybe my wife that gets upset that I spent money on it. But when you're talking about 2-4 people in these things, you cannot simply say, worst case, what'll happen? So the stringency of taking these aircraft through certification is significant, and it's never been done before. What we're doing is also never been done. There's never been an electric aircraft that's gone through certification. But everybody knows what a boring-looking fixed-wing aircraft looks like and operates. It takes off from an airport, lands at an airport. The regulatory authorities know how to deal with it. The fact that it's electric propulsion, that's new, and we'll have to deal with it. But it's different from an aircraft that have never been designed. It has no ability to glide. It has no ability to auto-rotate, which is emergency land like a helicopter does, because the propellers are too small. So that's just the technology side of it. Then there's the whole aviation management. We all know, and we've known for 70 years, how to manage planes between airports and flight paths. We know how to do that. We also know, by the way, how to manage traffic on roads. Cars can't go wherever they want. They're limited by lanes, etc. No one knows how do you control these types of vertical takeoff and landing vehicles in the skies over a city. That doesn't exist yet. So that has to be overcome. Now let's add the third part, which is the complexity of flying them. A lot of these companies are saying, oh yeah, we're going to solve that with autonomous flying. Well, now there's a third technology that has to be created, autonomous capability, with tens of other of these, if not hundreds of others of these, flying in the sky with families in them. So these things, while they will be overcome and solved, we think it's about 10, maybe even 15 years before we really see them operate as intended. We may see some sooner operating from an airport to an airport, but then it's not really an air taxi, it's an electric aircraft.
So Roei, we have there's a question in the chat here. What's the ROI with the Beaver or Caravan?
Yeah, so I clearly won't give you what it's costing us to do this first plane, etc. But here's what I'll let you know. For the operator, like Harbor Air, if you look at flying the Beaver or a Caravan for 100 miles, it costs around $350 to $400 in fuel. I'm not talking about all the other costs that are the same. The pilot, right? Both planes have a pilot. Both planes have to pay to land at the airport, etc. But about $350 to $400 in fuel for 100 miles. It costs $4 in electricity. So now think of the ROI. Think of an airline, a company like Float. They're a company now that's a new startup in LA. They're trying to solve this traffic jam issue, not with a futuristic vertical takeoff and landing, but with an airplane they can get today. They're actually doing it, guess what, with a Cessna Caravan. It's an internal combustion Cessna Caravan, a regular Cessna Caravan. They're charging for flights between northern to southern, eastern to western LA, between $35 to $40 a flight. That's amazing. That's unbelievable. That's as cheap as driving and spending an hour and a half in traffic. 35 to 40 bucks. You can look them online. Float. They're called Float in LA. But if it's costing you $350 to $400 just in fuel to fly 100 miles, guess what? Their ROI probably isn't phenomenal. But imagine if it was $4 in electricity. Imagine if instead of 1,200 bucks an hour, as I was mentioning before, it was 200 to 300 bucks an hour. Now, with 6 people each paying 35 to 40 bucks, you're making money instantaneously. And so the ROI is very significant when it comes to operating these aircraft when you compare like to like internal combustion to electric.
Awesome. Yeah, I think the ROI is going to be in the operations. I totally agree. So there's another question here from Ajay. What is the anticipated price of the Eviation 9 seater aircraft when it's launched in a couple of years?
Yeah, so I think the price that they said at the Paris Air Show was like 4 to 5 million, something like that. If you think about it, the goal of these aircraft is to be the same price as an equivalent aircraft of that stature, right? So if you look at this type of aircraft, compare it to a PC-12 or a high-end Beechcraft 300, they're going to be priced about the same. Maybe the Eviation Alice will be even priced a little bit higher for a premium, like the Tesla costs more than maybe a high-end Toyota or a Lexus or something like that. So you may have a premium there. But remember that usually for airlines, the upfront one-time cost of the aircraft is insignificant, or to put it more accurately, very low compared to the ongoing daily cost of operating that aircraft. So imagine if you're buying the Alice for about the same as a high-end aircraft that is equivalent to, maybe even with a little premium. But instead of paying 1,200, 15 bucks an hour, you're paying 200 bucks an hour. Again, your operating costs and your ROI over the life of that aircraft, tremendously different.
Yeah, that's exactly how Tesla sells too, right? They give you
exactly. Again, I have a Kia Niro. We used to have a Kia Soul electric with 110 miles range, and now we switched to a Kia Niro electric with 280 miles range. When I took the Kia Soul the first time, I knew in my mind that you don't pay for fuel, right? You know it. It's an electric car. But until 3 months passed, and I thought to myself, my God, I have never been to a fuel station. I've never gone to Costco to fill up. It's amazing to think about those cost savings. Yes, I still pay for electricity when I charge, but it's peanuts compared to the fuel. So that's one part. The second is the 3 years I owned the Soul, never been for service. There is no service, right? There's no spark plugs, filters, oil. That doesn't exist. Same thing with airplanes. Traditional internal combustion engines, these Cessna Caravans, the Beavers, etc., let alone the jets, but even the propeller planes, every 1,500, 2,000 hours, they need to overhaul their engine. Basically, take it apart and build it back together. That costs about 80% of buying a new engine. And they have to do that every 1,500, 2,000, 2,500 hours. So that's, depending on how you fly, every year to 3 years. With an electric motor, there's no such thing. There's no friction, there's no oil, there's no lubrication. There's one moving part, not hundreds, one moving part. And so just like an electric car, the service is minimal, the maintenance is minimal, and the cost to operate is minimal.
Yep. So here's another question. What is the status of electric training aircraft?
Yeah, so there are a few companies out there doing that, small 2-passenger aircraft. One is in Europe called Pipistrel. The other is right here in the US in Denver, outside of Denver, called by Aerospace. The both of them have developed 2-passenger aircraft. In fact, Pipistrel just certified it's still certified as a light sport aircraft, but certified their first aircraft here in the United States. And so there are already flight schools that have started to order these 2-passenger, 2-person trainers. They have usually about like a 20-minute flight capability. They fly up to 500, 1,000 feet. They're built basically to fly, circuits around the airport to train pilots much more cheaply and economically, let alone not creating any emissions. And so I think those are phenomenal. We don't deal in that at all. Those motors deal in powers of 100 horsepower, 90 horsepower, 120 horsepower. Our smallest motor is 375. And so we really don't deal in that, but we love it because, again, just like the cars started to teach people what electric transportation could be, these small trainers are teaching people what electric planes could be. So we just love them, and they're flying.
Yep. So next question, Kyle. Actually, this is one of the questions I had as well, and get quite a bit of this, and it has to do with charging the battery and the turnaround time, because a lot of, as we know, a lot of airlines have short turnaround times. How do you solve that problem, or how do you expect to solve that problem?
Yeah, that's a really good point. So there's a few parts to that answer. The first straightforward one is we're going to be using, or airports can choose to use, let's put it that way, as airlines can, superchargers, very similar, equivalent to what Tesla has, 350, 500 kilowatt chargers. If you use that on these types of airplanes, you can get to a 1-to-1 to 1.75, a 1 to 0.75 ratio, meaning 30-minute flight, you charge for 30 to 45 minutes. So it's not as fast as, you can fly on a Southwest airplane for 2 hours and they'll turn it in 20 minutes. It's not even close. But 30-minute flight, 30, which is about what this thing will do, or hour flight at the extreme, and charge it for an hour to an hour and a half, not bad. That's one part of the answer. So using those fast chargers. You use, of course, a regular charger or even a home fast charger, it'll be much slower. But the second part to that answer, and there's three parts. The second part to that answer is many of these airplanes that we're going after, the Harbor Airs, the Kenmore Airs, the FedEx cargo operators, right? All these small propeller planes, they don't do the 20-minute turn like Southwest does. They fly for 30 minutes and they're on the ground for 45 minutes to an hour. If you're a FedEx or a DHL or a UPS, you fly for 30, 45 minutes and you're on the ground for 4 hours. Because what's the model? You fly the packages, right? The big airplane comes to the main airport, offloads all these packages. They load them onto these small propeller planes. The small propeller planes will fly 35, 45 minutes, an hour to the small sub-regional airport, land there. They take the packages, put them on trucks, go deliver. Now the plane waits 4, 5, 6, 8 hours until all the trucks come back with all the pickups that they did. They load the plane flies back to the big plane at night, loads the big plane, the plane goes, and that little propeller plane sits there overnight now. Mm-hmm. And so a lot of these aircraft are already flying in their business model in a way that suits the fact that charging is slower than fueling. And so there's no real big change. So that's the second part of the answer. The third part, why does Southwest do what they do? Because the cost of that aircraft and operating it is so expensive, the only way to make money is those quick turns. No catering, no service, load everyone on the bus as fast as possible because that thing is costing them money every minute. Same thing on some of these propeller planes, even the ones that do faster. They're not fast, but faster turns. But what if your airplane costs you 40, 50, 60% less to operate per hour? Maybe turning in 20 minutes, you might say, you know what? To save 40% for my bottom line, to go to 40 minutes, I'll wait. And so that's the third part of that answer. So again, batteries are not as powerful as fuel. Charging batteries is not as fast as fueling. But when you look at the overall economics of it and the business models, it actually works.
Yeah.
With such a large surface area available, why can't we use solar cells on them to trickle charge them, when you're waiting during those 6 or 8 hours, like in the cargo, like the FedEx planes and stuff?
Yeah.
Or even otherwise during the day?
Yeah, it's an interesting idea. Solar panels have such a low power density, or the ability to create such low power density compared to the weight of the panels in the system, it's not worth it. There's no way you could justify it. If you look at the only solar aircraft to have flown around the world, and you look at the size of that thing, for the 2 people that it could take flying at 60 miles an hour, it just isn't worth it. Now, with that said, where does the solar panel or solar idea come into play very strongly? Together with wind or hydro at the airport. So imagine this, the airplane lands at the airport, and now instead of connecting to the grid to charge, what if we had a Bowser or a mobile battery pack on a truck, which by the way, we've developed. You had a mobile battery pack that was already full of electricity. That battery pack drives up to the plane, charges it very fast because battery to battery is faster than grid to battery, charges it fast. Now the plane is full, can leave. The battery pack, let's say it's empty. What does it do? It can now go aside to a large, much larger farm of solar panels that doesn't have to be lightweight because they're on the ground, and it can trickle charge there at a significantly low cost. Or it could go off to a wind turbine, or it could go off to a dam where there's hydropower. It could drive there, charge up at low rates, trickle charge because there's no hurry, drive back to the airport and fill up. Now you might say, there won't be enough with all these planes. There's not going to be a million of these aircraft. Remember, we're talking about replacing having to fly SeaTac to Portland or SeaTac to Pullman with being able to fly Arlington to Walla Walla. It's not going to be 50 planes an hour doing Arlington to Walla Walla or going to Arlington at all, or to Snohomish, or to, all to Bend, Oregon. You'll have one plane an hour, one plane every 2 hours. How many people are going to fly specifically into Bend? Enough to justify a 9-passenger aircraft, but not to do it 10 times an hour. And so the idea of being able to trickle charge off airport or the side of the airport at really low cost of power, hydro, wind, solar, where it's possible, which means now the entire value chain is truly clean. Being able to do that and then come to the airport and charge when needed is definitely one of the models that we're working on with airports.
So we're right at 7. There's 4 more questions here. Roei, how much time do you have?
Shoot off, and I have about 15 minutes.
Okay. So Samir asks, this is about the Alice aircraft. It has high charge time to flight time ratio. Will you be able to reduce the charging time or allow swap of the batteries to minimize the time on ground? I think you've kind of answered this question, but are you doing anything specific for Alice?
The charge time is actually, as I mentioned, a 1-to-1 ratio can be done when you're using superchargers, high capacity fast chargers. Second is on an airplane like the Alice, you won't have one charging point, you put 2 charging points. So then you can have 2 chargers, charging them at once, reducing that time by half. The idea of swapping batteries is not very realistic. It works on the small trainers that someone was asking about, because they're so small and such a little battery for so short flights, you can actually come in and swap them. The challenge with aircraft of this size, 5, 9, 12 passengers, you're talking about literally a ton or more of batteries. These are 800-volt batteries. I don't know about you, but I don't want an airplane mechanic having to now take apart and touch an 800-volt battery and trying to install it back that weighs a ton. That means that while you're doing that, they have to be somewhere to the side of the airport, not next to any people. It has to be done by a certified electrician with some sort of contraption that can take a weight of a ton of 800-volt batteries and move them around. And you can't be near that aircraft. The time savings there isn't big if you compare it to charging it like my teenage daughter can charge my electric car. She just plugs it in. So you can imagine a plane arriving, plug it in immediately to start charging. Then the passengers or cargo can be taken off. The pilot can do their walk around the aircraft for safety. People can load. And the last thing you do is disconnect from power. And so when you compare those 2 models, the time difference isn't that big.
Perfect. So next one from Ajay. Any small electric planes in the works, 2 to 4 seaters to replace the family car?
So those are the kind of, I'll call it VTOL, vertical takeoff and landing things that have been developed. There are about 170 companies working on that. It's a very sexy proposition, right? I like to joke that MagniX and Eviation are in the most boring part of aviation. We don't fly transatlantic, transpacific. We don't go supersonic. We don't hover and fly in between buildings. We take 5 to 12 people between an airport to an airport. We just do it at really low cost, really high efficiency rates with 0 emissions. And so there are companies working on those things. We'll see what happens.
Yeah, that's a lot of companies. Okay, next question. How soon do you expect to have your motors certified for commercial flights?
We plan to have a certified propulsion systems by the end of 2021, so a little less than 2 years from now. We've been working on it now for with the FAA already for over 8 months. So another about 2 years by the end of 2021 certified. And so 2022, you should be able to buy tickets and fly on airlines like Harbor Air and happen to get on an all-electric plane.
Awesome. Okay, next question. From Tamer. I understand that Alice was built and showcased at the Paris Air Show. What's holding Alice back from test flights and in-service flights?
An aircraft is a very, very complex system. The aircraft was debuted there, but it didn't fly, right? We powered on, but we didn't fly. The integration of an aircraft with all its parts and all its systems and preparing it for flight is a very long, cumbersome process for good reason. Safety, right? You're talking about even if passengers won't be on it, there'll be at least one pilot on it. So we want to be 100%, not 90%, not 80%, 100% sure that this thing will fly. Before MagniX, I used to lead a software company. And, with software, you can release beta, right? Yeah, it has a few bugs. Maybe it'll crash. Who knows? And then we'll update it. We can't have that in an airplane. There's no such thing as a beta airplane or a beta propulsion system. You can't say, let's release it. I know there's a few bugs. Maybe it'll crash. No, it has to be 100%. And so these things simply take a long time. That's why we're hoping the Alice, the plan right now is sometime next year to have it fly.
Awesome. Okay, Samir has a question. Samir, maybe you can hop on to ask this. I don't know what the acronym is. TBO. Do you understand that? What is the TBO hours of the motor?
Right now, we're planning for 10,000 hours TBO and a 30,000 hour life. But the term TBO, time before between overhauls, which is kind of what I mentioned before, you have to take the internal combustion engine, break it apart, put it back together, basically, because of all the friction and everything that goes in that system. An electric motor is kind of like a Tesla, a washing machine, or a mixer. There's not a lot that goes wrong there. It's a very simple, once you've cracked the code of how to do it like we did on the motor itself is pretty simple. And so we don't expect the overhaul to truly be an overhaul. Now, we'll have to prove it to the FAA, et cetera. But we expect that after 30,000 hours, we look at the motor, test it, and say, great, keep going. And that the FAA will agree to that once we've proven the system. And so it's very different when you think about what time between overhauls is between an internal combustion engine and an electric motor.
Yeah. Okay, so last question. I have one related one. Where are you, this is from D, where are you spending time as a business? What do you need next? And my question was kind of related. So one of the things that we do as part of the meetup is to connect local companies with folks who are looking for jobs. Are you hiring? And if so, where can they go look it up, and what sort of roles are you hiring for?
Yeah, so first of all, yes, we're hiring. You can go to our webpage, and we have a link there to what we're looking for. We're looking, for example, for people, software developers who know how to do, for example, FPGA, kind of low-level software right into our hardware of the power electronics. So FPGA type software capability, high-level software as well for our power electronics. So we look for folks like that. Airplane engineers, folks who have aero or aviation experience on aircraft, propulsion folks, rotor dynamics engineers who are good at stress and rotor dynamics, fluid dynamics, so stuff like that. We definitely look for good folks all the time. And there are openings that you can see, as I mentioned, on our website, www.magniX.aero, A-E-R-O. In terms of where do we spend our time, there's a few key elements. One, continuously challenging our own status quo. It's one of our values as a company, is to continue to challenge status quo, and that includes not just the industry's status quo, which clearly we're questioning and challenging, but even our own. So we've flown, right? We're flying the Beaver. Let's make it better, lighter, cheaper, stronger. And so we take lessons and continue to iterate and reiterate our propulsion systems to make them better and lighter for the customer. So that's one thing we do. Second is, of course, all the work, and it's a lot of work to go to certification. Everything from basically what we have to do is design, build, and test the propulsion system as a whole and the components of the propulsion system to be able to prove, one, of course, to ourselves, but two, to the FAA, that this system is as good, as reliable, as safe, at least, as what's out there today. Now, we believe it's even more so, but we have to prove all of these various and pass through all of these gates to prove that. That's a lot of work. So that's the second thing we do. And then the third is work with various customers on integrating these systems onto their aircraft, be they conversions or retrofits, what we call magnifications of existing aircraft, or new OEMs that are designing aircraft from scratch to be electric.
Awesome. I like that magnification. I think that was it. That was it for the questions. And we're actually right about on time. Anyone else? One last question, or we can call it an evening. And thank you so much, Roei. This was awesome.
It was my pleasure. Thank you very much. And let the electric revolution continue.